car engines get hot, they don't always convert everything to the work.
It's the high temperature reservoir
Heat
going
losses.
into the heat
So,
engine. The middle
and that's
one is the
composed
workout.
of your efficiency. So your efficiency of the system will be thermal efficiency is equal to workout over Qn. And that's where the second law is a few sort of theorems that we compose and say, well, this is not possible, therefore I'm going to have a thermal efficiency that is always going to be less than 1. It's not a straight transfer from heat. So if I have no rate of change of the system, nothing coming in or nothing going out, think of your piston engine. I'm putting in heat and it's going to equal to work. Well, it's equal to work multiplied by its efficiency and some heat output as well. So if I'm trying to apply this specific equation to it, it will be Q in is equal to work out plus Q out in order for it to be realistic. So what does that mean about my system here? It's going to look something like this. T hot. I'm adding Q in to my heat engine. I'm going to get work out, but I'm also going to get Q out, which goes into some T cold of some sort, which in our case, if you think of your car engines, it's just simply your ambient reservoir. So, and that's when thermal efficiency is less than 1. So that's one law that we have to take into consideration when we're going from hot to cold. Not everything is being transferred to warm. Now, how does this relate to propulsion systems? It's your component efficiency inside of propulsion systems, and we'll address it in a second. Now, there's also, can I do the opposite way? Start from a cold system, which is, let's say, ambient condition right now, go backwards.
If it's a reversible
You have to put work in, and that's a good point. So you can't just, so that's another law, sort of, that's part of the second law. So if I have T hot, and I go Q, I could go to a cold system, or T cold, or T low, if you want. But this, cold, this is okay. This is impossible. And like your colleague mentioned, well, I have to go and put some kind of work in. If I want to go from cold to hot, I have to put, to do that rate of heat transfer. Heat transfer wants to go from hot to cold. We're going the opposite way, so I have to put in work in. And that's another sort of clause as part of the second law that says you can't just go forward and backward with the first law of thermal. You actually have to restrict that first law. Makes sense? So with that, that's where the entropy actually comes in. So irreversibilities. Once you go from a T hot to T cold, I can't reverse the process back. I can't just go backwards. I have to do a work in. And by doing that work in, that's an energy that is lost, that I can't get back anymore. So although it moves from one way to another. So accordingly, we have to define irreversibilities. And say irreversibilities make it impossible to reverse a process resulting in a return of the system. To original state. So there's different sources of reversibilities in general that you have to account for. One of them, one of the major ones that we have to always work with is essentially friction. That's one of the sources of reversibilities. Think of your piston. I have friction right here. When I'm inducing heat, Q in, and I get work output from that piston, not everything is going towards work, like I just said. Not 100%, so there is losses, and these losses are in terms of friction, and that friction becomes heat. Also, by having a temperature difference, simply think of a heat exchanger. If I have one channel here that is T hot, and a channel here that is T cold, obviously you can isolate them as much as you can, but by nature, where does heat want to flow? It wants to go from top to bottom. So you can't control this process. You try to minimize it as much as you can, but in a sense, if you have two tubes at two different temperatures, most likely you're going to get Q losses. So think of your car engine. Your ambient temperature is lower than the combustion chamber temperature or the gas temperature inside. So by nature, the engine wants to lose heat. So not all the work is being converted just because of heat transfer. It's a heat transfer as part of your irreversibility. So heat transfer. So that's another irreversibility. Also, non-equilibrium conditions. So that's another one. If I have so that's another source of irreversibility. Well, how does this come into play? So think of your piston right here. If I am applying work on this piston, what's going to happen is the pressure here is going to be high, and the pressure here is going to be low pressure. That, as a result of this, you're having a inhomogeneous process as part of the compression. You want a uniform pressure distribution within the piston itself. So having these two pressures means that this system is not at equilibrium, and there is some irreversibilities associated with it. And it's by nature, by having that piston come in, your pressure is going to be highest where the piston is versus where the downstream and closed end would be. So these are some of the non-equilibrium characteristics that induce irreversibilities. Now, just want you to understand them, that these are sources of irreversibilities, but we're going to take it into consideration through efficiency of the system. So, one of the, we could say, part of the consequences of the second law one, all totally reversible cycles operating between the same thermal reservoirs have the same efficiency. which we already know what is the ideal efficiency. Well, yes, but it's the Carnot efficiency. Carnot cycle, if you remember from third law. It's just, yeah, which what most of you said, well, it's just one. Okay. And that's what we actually compare it to most of the time, which is your Carnot efficiency. Now, the second thing is all irreversible systems, or all cycles or systems will have a lower efficiency. Than a reversible cycle for the same T cold and T hot conditions. So meaning eta irreversible is going to be less than eta of the reversible system, which this reversible system is equal to 1. Okay? These are just bounds that we are trying to apply the second law to the first law by, just rules. And the third one, it is impossible to have a cycle efficiency that is greater than the Carnot efficiency. So Carnot efficiency is equal to 1 minus Q cold or low relative to Q hot. So efficiency, you can relate it through temperatures and say Q low relative to Q hot is equal to T low relative to T hot. So from that, I can get my efficiency of the Carnot is equal to 1 minus the T cold over T hot, which is going to be the maximum efficiency I can get out of that system, because I'm saying all my direct heat transfer is converted into 1 to 1. And that's the maximum efficiency that we have. Hence, that's what brings entropy into the equation. Okay, we're going to have to stop. That's what I was hoping not to get to this stage. So we're going to have to stop, and we're going to have to do entropy next class. Doesn't help, but revise those. What's the thought process of the conservation equations? I was hoping to sum it up in one lecture so you have it, but go with it.